Yes.
So we will take a look at recommender systems. Actually, I'm just going to go directly to a Jupyter notebook. I'm going to go directly to a Jupyter notebook. Okay, let me share the screen. Right, and let's just create a new notebook. Right, there we have it. So this is, I already have this code on the GitHub, so I'm just going to go ahead and get it from there. Okay, so machine learning foundations, and it's basically this one. This is the example. So if you remember, on Tuesday or Monday, sorry, we started talking about reinforcement learning. You can reference back to that video. I went over all the lecture, and in particular, I discussed an algorithm called Q learning. Okay, there are other algorithms in reinforcement learning. In fact, reinforcement learning could be an entire course by itself, like a whole semester course. It's a very big topic. It has existed for a long time, decades, right? Many more than that probably. And when the deep learning came around, the neural networks that you've probably heard about, that we'll talk about after spring break, that component, that machinery of neural networks was added to the already existing framework of reinforcement learning to make it way more powerful. Okay? Way more powerful. But in this week, where we're just introducing the topic, we're not using neural networks, and instead we're just focusing on Q learning and reinforcement learning. So the example that I did in class was the frozen lake, which was very simple. We went over that. This one's a little bit more complex. It's called taxi, or taxi cab is the name of the problem. So I'll talk a little bit about it today. I'm just going to go ahead and copy it. And I'll copy this into the Jupyter notebook. Where was the So I'm going to copy this in here so I don't have to type it up. Okay. And so you can see that there's some code. So I'll go over the code. Let's take a look. Because this is my computer, it should run, I think. And actually, this may not be able to run on this, actually. Let me see. Oh, no, there it is. Yeah, it does. You see, that's the game. You see it, and it's basically a board game, right? On here. So let's think about it. It's like Frozen Lake, but a little bit more complex. It's meant to be a little bit more interesting. But that's what is so great about this. So what's happening in this game, really, one thing that you have to do when you're talking about reinforcement learning is you really have to understand these games, right? These board games. It really helps to understand how the game works and to get the intuition so that you can then understand the algorithm a little bit better, right? So that's what we're going to do today. I'll just go through the algorithm. It's the same one I described on Monday. There's only a few little things happening. If you remember, on Monday, I showed you guys what David and I, my student, we worked on a project with the plane. We were doing the same thing. We had the outputs here, right, with the code, and then we had the graphics here, only we had better graphics from X-Plane 11. Here, where I'm just printing out this grid, These are board games, basically. So taxi cab, what's happening here, the little yellow square is the cab, as you probably imagine. And then you have these positions, R, Y, B, and G. And the taxi cab is basically has a specific task. Every game, you randomly put the passenger in one of these spots, R, G, Y, and B. And then the taxi then has the goal of taking that passenger to one of the spots, R, Y, B, and G. You guys see that? That's it. So that's what the whole point of the game, but you don't give it any rules. You don't tell it, okay, to get from Y to G, you have to do this, left, right. No, you kind of have to let it learn on its own. So there's a period of training, and then there should be a period of testing where it now has learned the Q table, and now it just does it. Do you guys see that? Does that make sense, guys? So that's how it works. So you let it train for a while to learn that Q table, all those values, right? So what that means is if I'm in state here, then I need to, what do I need to do if I'm here? What do you guys think? So I know it's changing, but let's say you're in where the mouse is, right? So what would you have to do to get from Y to G? What are the actions? Move up, move right, up, right? And then right. And you probably noticed that it can't actually move right here because there's a line. And the line would indicate like a street, you know, a building or a wall or something like that. So it cannot go wherever it has these lines, it can't cross. It can only cross where it's got the colon, the dots. Do you guys see that? So now these rules are the rules of the game, right? So remember when we talked about this on, and it finished, I think. When we talked about this on, it's still going. On Tuesday, probably just maxed out. On Monday, when we were talking about this, we said that we had to create two things, an agent and an environment. And the environment just is a variable that, or a class, an object that captures the game itself. It needs to capture the rules of the game, the position of the game, and also the rewards. Remember that you're not going to learn if you don't have these rewards, okay? Or it could be penalties. So that's, you know, for instance, here in this position, if it moves to the right, it hits the wall. That should be a penalty or a very low reward. But if it moves up, it could get a small reward, right? When does it get a really high reward? When it delivers the pass. You see that? So it's going to learn, you know, okay, I was towards the left and I kept going right and up, and, you know, I got to the reward. So that's the idea. Is this clear? One tricky thing, probably one of the hardest parts of this, two of the hardest parts are, if you have a new environment, right, like a new problem, creating the rules of that game can be a little bit tricky. And then the second one is what is called the state encoding. So here, there's a bit of a thing going on. In Frozen Lake, you really just needed to know what square you were on. But here, it's a little bit more complex because you need to know what square you're on, but also if you're in a position Y, B, R, and G, right? And also need to know where you're going. So there's just more to the state. Okay? You see that, guys? So state encoding can be a little bit tricky. And so we have to think, you have to really think about how to do that. So today I'll show you guys a trick that's really nice. It's called Cube Encoding, which it really just depends on how many things you're looking at, but it's N encoding is probably the generic way of describing it. We'll talk a little bit about that towards the end of the class. All right, but anyway, I wanted to demo this, right? I wanted to demo the game first, and then now we're just going to go over the code. You can, of course, play with this on your own. You can also try AI Gym. AI Gym has more games than just this, right? So it's got a whole bunch of board games. It now has a lot of Atari games, and I've heard it's even got like 3D kind of games now. All right, so what's great about that is it gives you an environment that already has the rules, the rewards, and then you just focus on the reinforcement learning algorithm. because they're two separate things, right? But they interact. Remember, the agent would be the RL. The environment is this. So another interesting fun thing that you might want to think about is, could you have two agents playing against each other? And do you think that would be good for them? So think about it this way, right? So here the agent just plays against the game itself, right? So it's one reinforcement learning algorithm playing against the rules of the game. But you could also think of a scenario where you have one reinforcement learning algorithm playing against another reinforcement learning algorithm because they're both interacting with a game. And this could be like a game like chess, right? Where in chess you have two opponents. So you can have actually two algorithms playing against each other. And what might happen is, what should happen is that the algorithms, as they're playing against each other, because they should become really good, because their objective is to beat each other, right? So faster than a human, for sure. It could be, yes, because think one observation that has been noticed a lot. I'll give you the paper AlphaGo. So I actually can probably bring that up. So AlphaGo from DeepMind paper. You can look at these here. Here's AlphaGo paper. This is the YouTube documentary, I think. Anyway, one thing about AlphaGo is that they apparently noticed was that the master, the current human master, right? Lee Sedol, that's what I was looking for. I think it's called Lee Sedol, Korean person. That person has a style of playing. They have, if you read books on like chess and things like that, and you study the games, you will see that they all have, the style of this one or the style of that one. They all have their own preferences, which means that they're really good at a specific area. And so what happened was that they would let these algorithms, especially if they played against each other, et cetera, and they would sometimes develop the game of one of these masters. But as they did the analysis of what they did, sometimes they actually came up with something completely different. Like imagine like a whole new style of playing the game, And so that's very interesting because you can, for instance, when you're training, you can specify parameters to indicate how much risk you're willing to take, right? If you think when I was talking about the Q-learning function, I said these parameters tell you how much you trust the future versus the present, right? By giving the future term a higher weight or a smaller weight. You guys remember that I said that? So you can add more components to that linear sum of values that can be risk aversion. How much of a risk taker is this reinforcement learning algorithm? Is it really willing to try different things? So one easy way of testing this is just be more random, right? Be more random. So instead of just doing randomness in the beginning, try randomness even when you train. That's almost like saying be creative and think outside of the box, right? As we humans say, maybe thinking outside of the box is just us with our own knowledge, taking something and assigning some random values to some of it and see what happens. That could be thinking outside of the box. Why not? I mean, it's possible, right? I don't know. I'm not a neuroscientist, but I'm sure these are things that you can consider. All right, so that's what's interesting. So like I said, the thing is you create an environment and an agent and you play against each other or individually, right? So let's take a look now. So I have the algorithm here. So I'm going to go to the Jupyter Notebook, and I'm just going to start going through the code. So if you guys, I don't know if you guys have downloaded this already to your machines. Did you run it? Yeah, exactly. So it's probably not going to work directly. All right. You got to go to the Anaconda prompt. So you guys can probably see this. All right. So to get this to work, you got to go to the Anaconda environment. It's that here. And do pip install gym. As I said, gym is the standard, or if you like reinforcement learning, this is where you should start, right? Download AI gym and just start. This will bring in all the games that you want to use. So if we go, to AI gym, Open AI gym. So Open AI, I don't know if you guys know, am I wrong about it? It was Elon Musk that gave the initial funding, right, to create Open AI. So this is Elon Musk's not-for-profit thing to make, and so he gave the funding for this, and this is a group of researchers. All they do is like research AI, and it's Open AI to be open source, right? To counterweight like the Googles and the Facebooks, which are more proprietary. And they were working on reinforcement learning, and so they created this toolkit. GYM is a toolkit for developing and comparing reinforcement learning algorithms. Now, as you saw in the project that I worked on, we didn't use AI gym. We just used Microsoft, Explain 11 at the time. But one thing that we did before is we went through gym. So we went through gym like in a lot of detail and tried to understand the classes and how it did everything, right? So that we could build our own approach similar to how gym is built, so that our environment. So basically we have libraries to just talk to the simulator, and then we have one that just creates the environment. You know, we have different classes for different things. So we have agents, environments, and so on. But you can see GYM is a toolkit for developing and comparing reinforcement learning algorithms. It supports teaching agents, which is the RL algorithm, everything from walking to playing games like Pong and pinball. So as you can see, the current state of the art as of, I think, 2015 to 2017 is that reinforcement learning has already solved all of this, all Atari games, right? And it has solved chess and shogi and the other one, Go, right? Which are all board games. Go is supposed to be much more difficult than even chess, okay? And it's beaten the world master, world champion. As you can see, it does other things. Like here, you can see it's, you know, this is a type of flying. This is walking. So you can see that now it's got the 3D component for walking in AI gym. This is one that you can actually do in your own. If you want to try one, I would recommend that game, Cart Pull. It's basically a little cart, and it's trying to maintain a pole from not falling down. So it moves just to kind of balance it. Space Invaders and so on, right? And then here is some code. So this you can use as reference for your, and then there's the GitHub and the documentation. One interesting thing about, or one important challenge, as I said, one of the most difficult parts of any problem in reinforcement learning is setting up the environment. What are the rules? What is the reward? How do you say that you're winning or losing? So I want to stress this, because in chess, for instance, let's take chess or Go or shogi. It's very specific, right? You're at this position in the board, you make this move, you kill the queen, you put the king in check, you win the game. It's very specific, right? And so you can write those rules. But not every problem is like that. And that is a necessity for reinforcement learning to work, is that you have to have some kind of a score. So here, for instance, you have the score, you can use that as reference, you know, but there are other problems that are a little bit more difficult, but still, you might be able to use reinforcement learning. So for instance, this one, this is a spider, right? It's learning how to walk. But what if you want to teach that spider to dance salsa? Tell me, what's the reward function for dancing salsa? How do you even define that, right? It's incredibly difficult. So I'll tell you where the state of the art is, and that is actually very nice. I like what they're doing. Imagine that spider is moving like that, and it's learning how to dance salsa, right? So what it does is it just randomly dances like this for a little while, and then it dances like that for a little while, and then it dances like that for a little while. And you have those 3 instances in time, right? And basically all you do is, that's what's so great about this, is you can, for instance, for the upcoming example, you can just record that short clip. So on Monday, it did that for like 5 seconds, danced a little salsa. And then on Tuesday, it did another one, and they're all different. So as it's training over time, let's say every 5,000 iterations, it can request some human feedback. So it doesn't request feedback like every iteration, only every 5,000. It tried several things, 3 things, to keep it simple. And it just gives you this short clip. And it says, hey, here's a clip of me dancing salsa on Monday. Here's one of me dancing salsa on Tuesday. And then this one on Wednesday. Which one of these 3 do you think is best? That's it. And believe it or not, that technique is called reinforcement learning from human preferences. And it actually has shown great promise. So all you have to do then is you go and, oh, I think the Tuesday one. You're not even sure because again, you don't know how to define a reward function for dancing salsa. However, you know what you see, what you like, right? And so it's almost like you cannot explain it, but you know it. It's almost that thing that we sometimes say. I don't know how to explain it, but I know it's this. And so you click on that one, and when you click on that one, those weights that it was doing, right, are saved. And so then that becomes like what I was doing on Tuesday, that's a priority. I need to do more of that. Do you see that? And then now from there, it's going to try another 3. And maybe on the next day, it's going to just show you these little 3 clips, and you just look at them. And so if you think about it, out of 100% of the iterations that it's doing, you maybe end up looking at 1% of them. But over time, and that little 1% can make a huge difference for the reinforcement learning algorithm to learn. Because the reward function, so here you're not specifically defining the reward function, you're actually also learning the reward function just by giving it this feedback. Does that make sense? Is that clear for you guys? So I want you to see, I don't know if you take that technique plus the rest of reinforcement learning plus deep learning, those 3 things, you have something really incredible, right? And now all you have to do is model any problem that you can think of, any problem, logistics problems, war, anything that you want. Model it as a game, follow some of these things, make some simplifying assumptions, give it some feedback every now and then to even learn the reward function automatically. And, and so that I want you to hopefully take away that insight that this is not just for games. This is beyond that. As all you have to do is be able to frame, dancing salsa, what could be more abstract, right? Frame any problem as a game, and then try to follow this out. Okay. All right. So that's kind of what I wanted to say about that. Now let's just go to the code. Let's go through it. And we know it works. So you can see here, this is the AI gym library. So we import gym, then we select taxi version 3. There are other versions. Here, you're just playing with this. So basically, all the way to here, you're just kind of trying it out. You're just, getting a feel for what's going on. So here you have, look, you have the environment, and then you render. Okay, the board basically, you reset it to clear it, then you render it again. Okay, and then here it shows the environment. You can see the number of actions that you have and the observation space, which this observation space is actually quite big, right? And that's what I was talking about, that we use this encoding function to kind of say, you know, what the actual state is. But it's a state made up of 4 things, not just one. So it's not just like the position in the board anymore. That's just one. So this would be like from the first one would just be the position on the board. So like in the example of Frozen Lake, this would be values from 0 to 15 or 16 values. But then you have other things that you also work in there, right? And this is what I was talking to you that is called, I call it Cuban coding, but actually it should be called N encoding. And it's kind of it's a state representation that was developed for that is used in taxi cabs. Let me get. So we'll talk a little bit about that with something simpler than taxi cab is actually a little bit hard to understand. So let's do something simpler to understand the encoding. So usually because this will be, if you ever do reinforcement learning, right, you will have to do this. You will have to figure out what are the states that I'm going to use. Now you can treat the states as features. That could actually work, especially with deep learning. That could actually work. But from the point of view of the Q table, let's take a look at the state representation. So we're going to go to the whiteboard here. And when we did the Frozen Lake, we just had 16 states, right? Was it 16? 4 by 4, correct? So 4 by 4. So we just had to know where we were. Yeah, 4 by 4 is 16. So really, when we're representing the states in the Q table, you know, we had, I think, 4 actions. So the actions are here. So it's, you know, let's just say A, B, C, and D. These are the 4 actions. And then here we have which state we are in. So this is the same as the PDF. So the actions are actually always kind of straightforward, right? They're kind of easy. But then the states are a little bit tougher to think about because you have to do that really well. If you do the state representation badly, it's not going to work very well. So in a board game, so the best thing is to go through a lot of these and kind of figure out how they work, right? So here we have these. So now I'm going to change color here. And basically, what does this mean? If I'm here, that's a state. So let's call it 1, then 2, then 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Boom, done. So what that means is the states are 1, 2, 3, 4, and this would be 16, 15, ... You guys see that? So if you're here, you're in states. Okay, let me use another one. If you're in 4, you're in this state. That's how that corresponds, and then you know what actions to take. If you're in this, let's say in position 15, then you're here, and that's the state that you're in. You guys see that? And that's pretty straightforward. But sometimes you need to have more information than this. You need to know, for instance, let's just say for the sake of argument, that there's another type of information about the state of the environment, such as wind, no wind. If you remember, this game has wind or no wind as a parameter as well. So let's say that you walk, there's a hole here, you walk here, this is ice, but randomly, when you take this step, wind, strong wind, will push you to the left, so you fall into the hole. So that just makes the game harder. You guys see that? There is that encoding. So this encoding is 1 and 2, but it's on top of these. Do you see how it's on top of these, guys? And then there could be yet another third one that has from 1 to 100, ... Another type of state. I don't know that, temperature, right? So the temperature, so maybe the ice that you're on can melt. And so you can actually fall through it as well. And so these three things now have to be encoded. And now it is not so trivial, right? To figure out how to go, because this was pretty easy when it's just one. There's 16, boom, you're done. But now you have three things. And so that makes it a little bit more challenging. You guys see that? I'll give you another example. Go over here. Let's talk about flight. Flight, right? So flight, like the project I worked on. So an airplane, and you guys probably know this, flies on 3 axes, right? So this one, that one, and there's one here. You see that? That's called pitch, roll, and yaw. So what that means is the plane will do this, right? And that is roll. The plane will do this. That's pitch. The plane will also, this is the nose, do that. And that's called yaw. Okay. And so these three things have to be accounted for, right? The position where, that's the state of the plane. If for the problem of just stabilization. Now, if you want to go to point A to point B, altitude, direction, coordinates may also be parameters. But let's just keep it simple at three things. So here's, another picture of that. Right, so if we look, we have one axis there, so the plane will do that. And then there is an axis here, so the plane goes up and down, and then there's the other one. So this is the other angle. So there's 3. So the roll will be that. Okay, so these 3, now think about it. Those are angles, right? So if the plane, let's say the plane is flying straight like that, but if the plane is doing this, it's pitching up in relation to its angle. Do you see that? So this would be angle 0. This would be angle at a maximum of 18 degrees. Beyond that, it is unsafe for the airplane. It'll lose lift and, could be dangerous or something. So if you do the opposite of that, you're going down way too fast. And if, you might break the wings or something like that. Do you see that? So this is really important. The question is, how do you represent these, right? How do you represent these values? So in one axis, we have these degrees, right? A maximum, let's say from plus 30 to minus 30. You see that? And then we have to represent just for that. That's the state that represents just the pitch of it. So one simple solution to this, because is to discretize it and not keep it as, real valued numbers, because that's too many states. You don't want to have, let's say that you took every degree as a state, that's 60 degrees. In that, that's too much. So what you can do is you can discretize it by just creating like segments, right? So one segment, another segment, like that. And then you discretize it. So if you're in between plus 15 and minus 15 and plus 30, that's one group, one state. You're in that one. Do you guys see that? Does that make sense? So now if you think about it, we have pitch, roll, and yaw, and we want to represent the state. Based on the degrees, we are going to get the degrees obviously from the plane. Airplanes have indicators, right? They have gauges and stuff, and those gauges are going to tell you the degree that you are in relation to 0 degrees. So let's say that it gives us that our angle is 18. So then 18 falls within this block, right? So it's going to be that segment. So let's say that I divided this, the pitch angles from -30 to 30 into 9 components, 9, what we can call bins, 9 bins. So now we represent this as 9 bins. So 1, 2, 3, ... until 9. Does this make sense? And then now I have a way of saying, just by indicating the number, which position I'm in the pitch direction, right? I know if it's 18, I'm probably, let's say, in the 8th bin or the 9th bin, depending on how you did it. Is this clear, guys? Now let's do the same for the other roll and yaw. They're very much the same, right? So this is roll, actually, in this axis, right? So the same, or actually we can look at it here better. So the plane should do that or that, right? So, you know, upper, you know, the wing like that, right? That's called a roll. We're going to do the same thing. It should be limited to a certain degree. Let's say -30 to +30 again. That range divided into 9 bins. Why 9? Why not? So again, 1, 2, 3, 9. And then let's say you fall into -10. So that's probably bin 3, whatever it is. Got it? And then we do the same for yaw. And we just set that yaw is 1, 2, 3 to 9. We keep it consistent. So if you see, I've created this, which is actually pretty similar to this. You see that? Only those 3 have different, same values. Here, this one has 16, this one has 2, this one has 100. Do you see that? Now, how do we represent states? Because we said that we want the number of states here, right? We want, like, if this was 16, we want it 16. But now we have the problem that we have 1, 2, 3 pieces, 1, 2, 3 pieces here. And we can have 1, 2, 3, 4, 5, 6, 7, and they can be different values. So how do we do it? Because we need to represent it as just one number efficiently. So this is where Cube Encoding comes in. It's kind of neat. I'm going to start here. So pitch, roll, and yaw. And we made it into 3. And this is just because this will probably be more easier to visualize. So 1, 2, all the way to 9. 1, 2, all the way to 9. 1, 2, all the way to 9. So any ideas? How do we represent, how do we bring all of these together and just represent it as one number? Any ideas? Mapping it to what? Yeah. Well, see that what you're saying is that's how we're going to learn. Right now, we just need to represent state. We're not even at a stage of real data. We just need to represent state. So the trick is, if you treat these as an axis and this one as an axis and this one as an axis, what can we do with these 3 axes? We can create a shape, right? An object. And that's why it's called usually Cube Encoding in this case, because it's intuitive to think that's 2 already. And that's the 3rd one. It's not a great cube. Yeah, go ahead. You make a shape, yeah, an object. So how? From 1, 2, 3 to 9. You got 9, right? So now let's say for instance here the value, I'm going to use different colors. So this one was 3, right? And this one was 7, and then this one was 5. Just picked a few, right? That's the state for the individual ones. Now in Cube Encoding, I can do, okay, the first one is 3, this position. Then here on this other axis, I'm going to use the same color. 1, 2, 3, ... 9. So then change to green. 7 is here. You see that? And then the last one is 5. So 1, 2, 3. You know, I'm going in this direction now, right? You guys see that, right? So this was this direction. This was this direction. It's a vector space, but it's an object in that vector space. So 3 to 9, the value is 5. You see that? Would you agree that if this is a Rubik's cube or a cube and you have these indexes, you're able to find the position in the cube, correct? If this is a cube, right? This is a cube, right? And I say we're gonna say the origin is right there, right? So 3 is about here, right? So about there. 7 would be like over there, maybe where that pillar is, sort of, right? And then we just do the last one, 5 going up. So maybe where that picture is, that would be 375. Would you guys agree? In this whole cube, we found one position that accounts for these 3 coordinates. Does that make sense? Now, there's another little technique that I'm sure you learned at some point when you were learning programming, that somebody told you to take something like this, a cube or 3 for loops, and make it into one number, right? And that's what you do. So from here, you can derive a specific number because this is now 9 by 9 by 9. That's the number of cells that you have in this cube, correct? Would you agree? That there's, what is this number? 9 by 9 by 9. 7 something? 724. Can you just do the math? 9 by 9 by 9. 729. That's the possible number of states that this can represent. And it actually efficiently represents the 3 by 7 by 5, right? So we can represent any combination of these states in this cube. And then we just figure out a way to take 9 by, this value and get the 729. Do you see that? So obviously this is not 729, right? This is going to be the number represented by 3, 7, and 5. This is just the total number of states. So now when you do the Q table, you know your Q table for that problem, 729. If your values are 3, 5, and 7, then now you can find maybe that it is that state. Is that clear, guys? Does that idea make sense? Now let's look at the code and how it's computed so we can take a look. That's actually, this is done by the environment itself just to keep it simple for you, right? So it's like a representation of each one, each index, and it goes in there. If we go to, and so now 3120 is actually state 328. You see that? So how is this actually done? For this, I'll have to go to my own code. Let's go to the GitHub. And here, I think. No, maybe not. Yeah, so, nope. Where is this? Oh, here. So, all right. So in this example, in the code and explain environment, you'll find the functions. You can see here, I'm saying 9 by 9 by 729. So cube, that's how what we were talking about. And then there's a function in here. Here it is. Encode state explain. So you see that it's very similar to the function that they have in code taxicab. I literally just copy pasted and changed the name, right? So But the trick is you provide pitch, roll, and yaw very much as I said, in a very simple way, because you just need to know the intuitive thing. You know, what are my bins in pitch? What are my bins in roll, or whatever the other problems are. But I encode them now. So I know that, you know, the maximum number of states is 9 by 9 by 9. So you start basically with the value, and then you just do a series of multiplications and sums, right? So you take the original value, multiply it times 9, right, to kind of arrive at the first axis, then add the next one. So this is basically the way it works. The best thing that I can tell you for this example is just try it out with different values, and it'll make sense. Okay, do you guys understand? So try it with different values of pitch, roll, and yaw, and it's just this formula, but by having the 3 values, it'll give you the specific position in the cube. Got it? And then the decode should be the exact, you know, kind of opposite direction. The code is a little bit more complex, but it basically takes a number like 328 and it decomposes it into the 3 values. Pitch, roll, and yaw. Got it, guys? So you got to play with this function. I mean, we could do this function. You can just copy it to your code and then start trying out, like print out what I is. And then, you know, pitch might be like 6. And then it's going to be 6 times the number of states, which is 9. And then it gives you a new value. And then that value plus what the roll value is, 3. And then you multiply it again. And so on. And that's basically the algorithm to calculate N encoding. And this, if you wanted to do more states, then you just add more of these. This could also be done in a for loop. So it's a generic function that works for different types of states, and the number of bins can also be changed. Okay. Any questions about this? Yeah. Bin is, you mean the number of values in the bin, or do you mean bin is just, yeah, so bin is, for instance, if we go to the whiteboard, right? We go to the whiteboard. What I meant by bin was this, that the range of the plane is actually from minus 30 degrees to plus 30 degrees. But I don't want to represent that pitch as a 1 degree, let's say, right? Because then that would give me 60 bins, rather as a group. So I'm going to limit it to, if it's from plus 15 to plus 30 degrees, if the gauge in the plane gives me that you're at 18 degrees, then you fall in the bin of 15 to 30. And that's represented by just, let's say, 7 in just the pitch group that has 9 bins. And you're just allocating the state to one of the 9 bins. You understand? Yeah. And so once we have these 3, we still have the problem that we need to represent it like this as a number, right? From 1 to 16. So because we have multiple, we need to make those multiples into one sequence. And so a solution to that is to do this, the cube encoding. So we treat, and this is easier because they're all the same. So it's easier to visualize this cube, the 9 bins of pitch, the 9 bins. So the 9 bins of pitch are in the y-axis, right? And then the 9 bins of roll are in the x-axis. And then the 9 bins of yaw are in the z-axis of the cube. Yeah, go ahead. Yeah, it works because then it's a cube that it's not a square cube, right? It's you know, you can have other kinds of cubes. It still works perfect. Now the only thing is, as I said, this kind of thing, you have to think of the algorithm. The algorithm here, it's very much hard coded, right? And here, notice every time I was calling bins, which is 9, the same variable, but in the case where it's a variable, each one is different, then these would have to be different variables. You'd have bin state for pitch, bin state for roll, bin state for yaw. Does that answer your question? Any other questions? Does this make sense? So for this, definitely, if you want to understand Cube encoding a little bit better, the best thing to do is just to try out these two functions. Okay, let's try them out. And play with it. So start, put different values in there and convince yourself that it will always return a value from 1 to 729. It's almost like, probably the best way to think about it is think of a hotel and the rooms in the hotel, right? It's kind of the same thing. You're putting in different rooms, right? So there's going to be the floor, right? That's the easiest one. What floor are you in, right? And then once you're in a floor, then you have like the x-axis, right? Are you in that room, which is going to be in that corner, or that room over there? And each one of those has a room number. Floor 7, room 2-1 versus room 3-2, whatever. You see, that's literally what you're doing. So that number is actually, if you're in floor 7, that's 721 or 733. You see that? Make sense? So that's the way to think about it. But obviously, you can be in a hotel that's n dimensional. More than 3 dimensions, right? That's perfectly fine. Got it? All right. So we're running out of time, but this was really the most important thing. I think the hardest part, one of the hardest parts actually of reinforcement learning is the state encoding. And I really like this method because it's like a universal state representation method. So any problem that you give me, I'm gonna first try to map the states like this. It's efficient. And I promise you, if you were doing this, you'd find it difficult if you don't know this technique. But with this technique, I think it's pretty good. All right, so what we'll do is, this is just play with this. This is the functions that we discussed. This is the rendering function. And then here is the Q table, as we discussed in the lecture on Monday. And then there's the main loop where you're going through the functions. So this is the training phase, right? So you're training here. And then once you've learned, evaluate the agent now that we have learned the Q table. If you notice, the difference pretty much between both algorithms is that this one has the reward function, the Bellman equation, which is the updating of the rewards. This one does not. And this one only reads the Q table and makes decisions. But you can only use the Q table after you have learned, right? Because initially all the values are random, and then that should be it, and then you should be able to get the little game. Does this make sense? Does this complete your understanding of reinforcement learning? Yeah. All right. Hopefully, right? Yeah. So we just spent the week on it. You could do your term project on this. I don't have a problem with that, but it would have to be a little bit more than this, right? Next, after spring break, we will start with, this is not homework, but I would suggest you run this code at home. When we come back after spring break, we will do neural networks, right? And that's pretty important. Yeah.
Do they have the code for the Atari ones on the chip so you can play with those?
Yeah.
Awesome. I want to check one.
Yeah, you can totally do that. So we can make that a homework if you want. You want that to be a homework? No? All right. Yeah, that's fine. So, but yeah, so you could play with the reinforcement learning and add, as you have seen, any game really, right? Any game that you want. But yeah, that concludes class for today. So I'll stop the recording.